All right. So this is going to be one of those short lecture days, and then we have a bunch of examples. Okay, and we kind of have two things that are going to hit that we're ready to do at the same time. So last time we talked about definite integrals, and we looked at a way we could find those as long as we could come up with an antiderivative. We mentioned that. So in this section, we're going to look at a slightly different notation that gives us a thing we call indefinite integral. But then as we do that, we're going to get the things we need to be able to do definite integrals as well. So we're going to have the ability to do definite and indefinite integrals here really shortly. Okay. And then we'll practice on those. Okay. And the assignment I just named calculating integrals, and it's got a mix of the two types together. And it's what I would call a double assignment. And it's 2 sections worth of problem. So we're going to do some examples on these. Okay. All right. So, pardon me. Okay, we're going to look at a way to write down a notation for antiderivative. Okay, and then it says review the formulas for antiderivatives. We're going to see those for the first time. Okay. And then we'll be able to use those to evaluate definite integrals. Okay. And then very, very, very briefly, we'll talk about what that means as far as net change. And that's not a very big deal at all. Okay. So, we had fundamental theorem of calculus last time. Okay, it says we've got a continuous function, getting like that, the integral from a to x of f of t dt. Okay. That's an antiderivative of f. Then we've got the second piece there that says if we've got the integral from a to b of f of x dx, we can find that by taking the antiderivative at b, evaluating the antiderivative at b, minus what we get when we evaluate the antiderivative at a. So we just evaluate the antiderivative at the 2 endpoints, okay, and we get the whole thing. Okay, we get the area underneath the curve. Okay, is one way we interpreted that. Okay. So when we've got numbers on there, when we've got endpoints, like a and b, on our integral symbol, we call those definite integrals. Okay, because we're talking about that integral from some number to another number. And so the area under the curve between those 2 numbers. If we're talking in general, okay, then we write the same thing, but we just don't put numbers on there. So we'll have the integral symbol, f of x dx, or we could say the integral of f of x dx, or we could say the antiderivative of f. Okay. In that case, when we don't have numbers on there, we call those indefinite integrals. Okay. And all an indefinite integral is strictly an antiderivative. It's an antiderivative. A definite integral is an antiderivative evaluated to give us some number. Okay. So slightly different there. So with the indefinite integral notation, we're saying the integral of some function is this. Or in other words, f of x is big F of x is an antiderivative of little f of x. Okay, what that one's saying. So, or in other words, if we take the derivative of big F of x, we get little f of x. That was part 1 of the fundamental theorem. Okay, just written a little bit differently. Okay, so more specific example. Okay. Here we could say the integral of x squared is x cubed over 3 plus c. We'll talk about this plus c in just a second. It's not a big deal. Okay. Because if we take the derivative of the thing on the right, Okay, so there we would multiply by 3, and then the 3's would cancel, subtract 1 from the exponent, we would get x squared. C is just a constant here, so if we take the derivative of a constant, we get 0. Okay. So these say the same thing, they're just written in different orders. Okay. Written in different orders. And x cubed over 3 is an antiderivative of x squared. But if we add or subtract any constant to that, we'll still have an antiderivative of x squared. Again, because when we take the derivative of a constant, it just goes away. We just get 0. So we could add plus or minus any number out here we want to, and we would still have an antiderivative. Okay, so to represent that, we just put this thing called the constant of integration out here. And our textbook uses a capital C for that. That's pretty common. Okay, usually you'll see a capital C to represent some constant. Okay. That's our derivative there. So really, there are multiple antiderivatives for any function because we could always add or subtract some constant value to it out there. Okay, so really quickly again, I kind of mentioned this already. But if we've got a definite integral, that's going to give us some number. If we have an indefinite integral, one without the limits of integration on there, we get a function or even a family of functions because of that plus C I did. And so two different things. The indefinite integral, we get a function. If we are plugging numbers in, if we have limits of integration, then we're just getting some number out of that thing. Okay. So if we're trying to find a definite integral, I don't care too much for how they've got this written, but if we're trying to find a definite integral, what we're saying is we're taking the antiderivative, the indefinite integral, and we got some notation here. We got a square bracket on the end. That means we're going to evaluate this thing between a and b. So really what I would prefer to have written there, I would like to see them have this, right? We got an antiderivative, and then that antiderivative we're evaluating between a and b. Same thing. So the challenging part for being able to do this is being able to come up with these antiderivatives. So the textbook has a section before we get here where they just talk about antiderivatives. And we haven't done that yet, so we need to talk about them now. So we got to have a supply of antiderivatives available to us to work with. So here's a big list. Okay, here's a big list. We're not going to use every one of these. Okay, so let me give you the ones that I consider most important here. Okay. We need to be able to use this rule. That's really just a property. And it says if we have a constant times a function, we can bring the constant out front of the integral symbol. Okay. This next one is really just a property as well. It says if we have the sum of two functions and we want that integral, we can find the integral or the antiderivative in this case of each function and add those together. Okay. And then we actually start getting some antiderivatives in here. Okay. If we need the antiderivative of a constant, it's just the k, there's our constant, and then it's just k times x. And all of these are going to have plus c. because you can add or subtract any constant value that you want to, and you'll still have an antiderivative. So antiderivative of a constant, we just add an x. So like the antiderivative of 3 would be 3x. And then we could add or subtract any constant we want to from that. The next one is like the reverse process for the power rule. And if you pay attention, it says this only works if our exponent is not -1. So this one will be the one that gets used most often, okay, just like the power rules thing we use most often with derivatives. It's just the reverse of the power rule. So it says we add 1 to the exponent, so n plus 1, and then we divide by whatever our new exponent is. And we're going to do plenty of examples. Just giving you the rules here. All right, why can n not be -1? Yeah, because then we'd be trying to divide by 0. That would be undefined, so we wouldn't get an antiderivative. So in the case we've got x to the -1, that's really 1 over x. So that's its own special case. Okay. We want an antiderivative of 1 over x, or x to the -1. On that one we get the natural log of, really the natural log of absolute value of x. And if you think about the derivative rule, right, the derivative of ln of x is 1 over x. That's just the reverse. And if you still remember the derivative rules on a lot of these, you're just working backward. Remember, e to the x is its own derivative. It's also its own antiderivative. So antiderivative of e to the x, e to the x. We're not going to worry about the general exponential, b to the x over there. We do want the basic sign, the basic trig functions. So I guess I don't want, so remember we got to go backwards. So if we've got sine of x and we're looking for antiderivative, okay, the derivative of cosine would be negative sine. We don't want the minus sign, so we got to put it over here. Okay, so the derivative of minus cosine would be positive sine. Then it gets a little bit tricky with the minus signs there. Okay. Yeah, go ahead and put this one on the list where we got secant squared, that's tangent. The other basic one, cosine's easier, which gives us sine. It's antiderivative. And that's it. That's it on there. Any of these other ones, if I wanted you to find the antiderivative, I'll give you the formula. Yellow one is the one you need to know. That's it. Okay. These things, if you just like Google antiderivative formulas or something, you're going to get hundreds of them. Okay, so you can't memorize all of them. So we'll just do the ones that come up the most. Okay. And then what everybody else in the world does. Okay, if you have some weird one come up, then you Google and see if you can find one that matches it. Okay. We use it that way. Okay. So how many is it? 1, 2, 3, 4, 5, 6, 7, 8. Well, really, the top two are properties. So 1, 2, 3, 4, 5, 6, 7. Not too bad. Okay. So With that said, we've got several forms of antiderivative that we can use. And the main thing that's helpful for, okay, yeah, we could just say, okay, if here's a function with its antiderivative, but the main thing we're going to use it for is finding definite intervals, okay, finding the area under the curve. And so let's do some basic examples, and then we'll come back to that. Okay. So let's see. So this one has got a polynomial. We want to find the indefinite integral from 4 to 6 of this thing. So we need an antiderivative, and then we can evaluate the antiderivative at 6, evaluate the antiderivative at 4, subtract, and we'll get the net area under the curve here. We'll get the indefinite integral. Correct, yeah. And we'll talk about it on this one too, why, if you want to. So we need an antiderivative. We can just take it piece by piece, right? We've got that property that says if we have a sum or a difference, we can split it into 3 separate integrals. We won't write it down. We'll just think about it that way. But we could write this the integral from 6 to 4 of x squared dx plus the integral from 4 to 6, I should say, of 3x dx plus minus the integral of 4 to 6 of 5 dx. We can do it that way. But we can just think about it like that. We don't have to write it down. So for the x squared part, we need something that when we take the derivative, we get x squared. Okay. If we were taking the derivative of that thing, if we were taking the derivative of x squared, what would we use? What rule? Power rule. Okay. So if you can get that, that gives you a good hint that you might want to think about using the reverse of that. Use the reverse of the power rule. So reverse of the power rule says we would add 1 to the exponent, okay, and then divide by our new exponent. So what was our coefficient in front? It was a 1. So if we divide 1 by 3, we get 1/3. Okay, the textbook will often write it like this. Okay, they're the same thing. You can write it either way you want to. Okay. So then for the next part, 3x, we can use the same technique. Okay, we can use like the reverse power rule, I guess we could call it. So we've got x. If we add 1 to the exponent, we'll get x squared. And then we need to divide the coefficient by our new exponent. So we did have a 3. And now we'll have 3 divided by 3. Okay. And then for the minus 5 part, that's just a constant. So we had that the first antiderivative rule just said we just add an x, add a variable. So that would just be minus 5. X. And if you want to justify that, okay, use the reverse power rule. We start off with negative 5x to the 0th. If we add 1 to the exponent, we'll get x to the first. Negative 5 divided by 1 is just negative 5. Okay. So there's an antiderivative there. That's just side note. Okay. And then what we want to do with this thing And then our notation we use is we'll put a square bracket. We want to evaluate this thing from 4 to 6. So these just stay in the same order as they were on the integral symbol. We evaluate it at the top one first, then put a minus sign, and then evaluate it at the bottom number. Okay. So evaluating this thing, we would have 1/3 times 6 cubed plus 3/2 times 6 squared minus 5 times 6 minus, and then we'll plug in 4 this time. 1/3 times 4 cubed plus 3/2 times 4 squared minus 5 times 4. And when we figure out what that is, we'll get a number, and that number is the net area underneath the graph of our starting function. So sounds kind of nasty to do by hand. You can just punch it in the calculator. Let's see this. 6 cubed. 6 times 6. What is that? 216. So I'll do it term by term, but I'm going to do it in the calculator. So 216 divided by 3. 72. And then 3/2 times 36. It's 54. And then minus 30. And then 4 cubed, 64. So that one, not quite as nice. It's 64/3. And then 3/2 times 16 is 24. And then minus 20. Okay, so term by term, that's what we get. But then let's see. So I'm going to do just so it's easy to follow. Okay, I'm going to combine these and then combine these, and then we'll have one subtraction at the end. Okay. So 72 plus 54 minus 30 is 96 minus and I get 76/3. The whole thing doesn't come out too pretty. We get 212/3, and if we wanted decimal, that's 70.6 repeating. We'll be happy with the exact value, but if you do want the decimal, that's what we get. Okay, not uncommon for these to come out not exact, because we are finding area underneath some curved shape. It's a little bit weirder for that to come out some exact integer than it is for it to come out something a little messier. Yes, it came from the parentheses, that's right. Yeah, so let's see. That part would be 4, so then we get 12/3 there, plus 64/3 gets 76/3. Do be careful with the signs. Okay. If you're gonna, you can distribute this minus sign to every term, okay, if it's convenient. Lots of times, though, it's convenient just to figure out this part in the parentheses and then subtract. Okay. This really depends on how the minus signs are popping up on that. Okay. So that's the fundamental theorem of calculus. It says if we find an antiderivative, which we did, evaluate it at both endpoints, subtract, we get the area under the curve between those two values, between 4 and 6. Okay. And that was pretty messy. Polynomials give you a lot of terms you have to evaluate, so sometimes they are kind of messy. Let's do another one that's kind of a little bit simpler when you get down to the last step. Okay. So we want the indefinite integral from 4 to 9. I mean the definite integral from 4 to 9. Square root of x. Okay. So do you remember when we were doing derivatives, what would we do first here? Yeah, change it to 1/2 power. So we can do the same thing here and it'll be helpful as well. So we can change it to the 1/2 power and then do the power rule in reverse, okay, to get our antiderivative. So if we add 1 to the exponent, a little bit tougher because we've got a fraction, but not that bad. If we add 1 to the exponent, so that's like adding 2 over 2. So we'll get x to the 3/2 or 3 over 2. Yeah. And then this part's a little bit weird. You could write it like this, right? We're going to divide it by 3 over 2. But then that's a mess to have to deal with actually figuring out the number. So we've got to take you back to like 4th grade here. We're trying to divide by a fraction. So what's the rule if we're dividing by a fraction? What can we do? Flip and multiply, yeah. So dividing by 3 over 2 is the same thing as multiplying by 2/3. That's a little bit of thought we had to put in things here. And then we want to evaluate this thing from 4 to 9. So we do the top number first. So we'll have 2/3 times 9 to the 3/2 power minus 2/3 times 4 to the 3/2 power. And most of the time you could punch that in the calculator and get it. We could also rewrite this as square root of 9 cubed and square root of 4 cubed. And I changed the 1/2 part of the power back to square root. Okay. You could take the square root part first and then cube it. If you wanted to, you could do square root of 9 cubed. That works as well. So let's see what we get there. So that'll be 3 cubed. That's 27. And then that's 2 cubes. That's 8. So again, you can just go to the calculator whenever you get fed up with trying to do it by hand. So what's that? 38 over 3. So 38 over 3 is the answer we want. A decimal approximation is about just 12.6 repeating. It's not approximation. A little more than 12 and a half. Let's talk about something else we could do that could help us sometimes. This one's not too bad. But when we get to this point, okay, so let me move this over here and we'll do it in a different color from there. And we can also, since we have a constant factor of 2/3, we know we're going to have that in both of these. And we got a 2/3 in this one and a 2/3 in this one. Okay. We can save that 2/3 until the end. Okay, we can like factor out that 2/3. So what we could have done, 2/3 times that part. Okay. So then we would have had 2/3, and then we would have figured out. So that's 2/3 times 27 minus 8. And then you get the same thing. Okay. But if you have a constant, you can factor it out front, okay, and save it to the end. Sometimes that's really helpful. You don't have to write down as much stuff. Okay. Okay. Yes, something I forgot to mention that I meant to. Let's think of a really easy one. Okay. So if we're trying to find the general antiderivative, okay, the general antiderivative, we add 1 to the exponent, divide by the new exponent, and if we're finding the general antiderivative, we get a plus c on there. But when we're doing definite integrals, we don't have to write that down, because what happens when we go to evaluate that? Okay, so that one's a half of 4, so that's 2 plus c, and then minus a half of 0, 0, plus c, and then what's going to happen? Yeah, it's going to cancel. So doing definite integrals, the constant of integration would cancel every single time, because you always got a plus c, and then minus, and then on this one you would have a plus c, so they're always going to cancel out, so you don't have to write down the plus c when you're doing definite integration. Okay. So if you got numbers on there and you get a number answer, you don't have to have plus c. Okay. It just saves you from having to write that much down. All right. Do one more here, and then we'll look back at the slides for a second. Okay. So for this one, we need an antiderivative of sine. You can either remember it or you can figure it out. I mean, that's something we can figure out. We got to have something that when we take the derivative, we get sine. Yeah, so minus cosine or negative cosine. Their antiderivative. And you can check it, right? If you take the derivative of negative cosine, you'll get negative sine. So that's positive sine. Okay. And then we want to evaluate this from pi over 4 to pi. Okay. Top number first. Okay. So if you're using your calculator on these, make sure you're in radians. Okay. So cosine of pi, you may know it without punching it. Yeah, -1 on that one. Yeah, 0 is 1. So we get that. and minus cosine of pi over 4. I always forget what that is. My trig's not real strong, so. Yeah, so that one is 0. So the decimal is like 0.707. So is that root 3? No, is it root 3 over 2? Root 2 over 2. Okay, that's right. Yeah, so we get minus root 2 over 2. I need to go back and take trig again. Okay. So I think we're okay with decimal answers on WebAssign. Let me double check, but the exact answer is 1 plus root 2 over 2. And that's like 1.707. Let me double check on WebAssign and make sure it's going to take a decimal answer. Real quick here. I think it will. Here for me just a second. I just don't want to tell you wrong. Might not. Let's see. Okay, so it's actually not going to take a decimal on those. There are only 2 in the assignment. Okay. So okay. So you might have to break out the unit circle or something like that on my homework. I try to give you something that comes out real easy on the test. And on the test, I also don't care if you give me a decimal. That's fine. So just be aware of that on the 2 problems that have trig. Let's see if the other one is even an issue. Let me look. Yeah, on the other one it's something real easy. So it's like sine of 1 or something like that. Okay. Comes out exact. All right. So back to the slides real quick. One thing that can also be helpful, don't worry about it. Okay, we're for these, okay, but something that is allowed. Okay, is if we've got something like this where we've got trig functions involved. It's okay to manipulate what you got inside the interval. And so, like this one, you could split it apart instead of having sine squared on the bottom. And you could do a trig substitution, and then this thing's on the list comes out to negative cosecant. That's not going to be a big focus of ours in Cal 1. Okay, but know that that is acceptable. And then look at this one. This is another good example because we've got some work we've got to do on it before we can find the antiderivative. So let's go back over to our scratch paper. So the one it gave us there is this. Okay, so thing inside of our integral, we call it the integrand. Remember, a little more complicated on this one. But really, we just have some algebra we need to do. The antiderivative turns out not to be too bad after we get it in a form where we can find the antiderivative easily. This one we just need to work with a little bit. We don't have a rule, especially right now. We don't have a lot of things to work with, but we don't have a rule that is like equivalent to the quotient rule with integral. So we need to figure out some way of writing this without that t squared in the bottom. We can do a few things here. So all of these are tricks that can be useful. One thing I'm going to do is I'm going to split each one of these terms up into its own term over the denominator. The middle one's got the most going on because t, the square root of t, how could we rewrite that? Yeah, so that would be t to the 1/2. 1/2. So we've got t squared times t to the 1/2. We can combine those. What's that going to be? 2 would be 4 over 2. So yeah, so this thing turns into t to the 5 over 2. We got to get a common denominator there. So it's t to the 5 over 2 over t squared. Last one's not that bad, thank goodness. And then we can do the division, right? Or we can just use our exponent rules if you want to think about it like that. T squared over t squared, that cancels. The middle one's a little bit of a headache again. What's our exponent rule if we've got a term on top and bottom? What are they? We can combine them by doing what to the exponents? Subtract. Yeah, subtract. So got 5 over 2 minus 2. If you need to, use a calculator. That's okay. 5 over 2 minus 2, that would be 5 over 2 minus 4 over 2. So yeah, we get t to the 1/2. So that simplifies out. But just be careful with the sign there. Okay. And then the last one, any ideas what we could do there? To get it into some form where we could find the antiderivative. So there's a way we could rewrite what, yeah, we can do t to, yeah, move it to the top. Okay. So then it turns out we only have to use one of those little things off of our list of antiderivative rules. We just use the reverse of the power rule to get the antiderivative. So getting the antiderivative is not too bad from here. So if we have a constant, we just add a variable. And then for the next one, we got t to the 1/2. So if we add 1 to that exponent, that'll be 3 over 2. And then, yeah, that's right. And then flip and multiply since it's a fraction. So 2/3. And then be a little careful on the last one. You have to be extra careful on the signs when you got a negative exponent. And so if we add 1 to the exponent, that's going to be t to the -1. And then right now our coefficient's -1. And if we divide by -1, we're going to get +1. So let me just put that out to the side too. So we get t to the -1, and we have -1 over -1. So we get plus t to the -1. And then we can evaluate that thing. Again, this one's got 3 terms, so it's a little bit more of a mess, but we can do it. We can remember to use the top number first. Okay. So we'll have 2 times 9 plus 2/3 times 9 to the 3/2. Plus, and if you want to on this one, you can write it 1 over 9. Or you can still do 9 to the -1 power if you want to. And it's minus. And I highly recommend putting the bracket so you keep the signs in the right place. This one's easier. Got 2 times 1 plus 2/3 times 1 to the 3/2 plus 1 over 1, which is just 1. I'm happy if you write that down and then go to calculator. I'm okay with that. You just be careful. Personally, I like trying to get the stuff out of the way I can do without a calculator, just so it's not so messy to type in. So 9 to the 3/2, that is square root of 9 cubed, so 3 cubed, so that's 2/3 times 27. This one's easy. We've got 2, and then 1 to the 3/2, so just 1. Okay. And then if it's me, that's probably when I would go to calculator. So 18 plus 2/3 times 27 plus 1/9. So that does not come out very pretty. And then let's see, that's 3 2/3. So 11 over 3. Yeah. And then let's see. Yeah, they're not pretty, but again, that's not unusual because we're talking about the area under an irregular shape, not the area under the curve. So. It's really probably more surprising that more of these don't come out irrational than they do. Questions there? Okay, so if we've got one of these like this, let me find this one. What's different on this one? Yeah, this is indefinite. We don't have numbers on the integral symbol. We don't have the limits of integration. So all we're doing is finding the antiderivative, and we stop. Okay. Here, let's see, we don't need that anymore. We add 1 to the exponent. Our coefficient was 5, so we do 5 divided by 3. On our next one, be careful because, especially with the negative exponents, it's easier to mess those up in my brain at least. So we add 1 to the exponent to get -1, and then divide our coefficient by -1. So it was +3, so it turns into -3. And then on the indefinites, we got something we got to remember on all of them. Plus c. Yeah. We got to remember our constant of integration on that one, so that's fine for that one. Negative exponent should be okay. Let me check. Make sure WebSign's not going to be picky about that. So let's see. Yes, and hold that question. That's a very good question. Okay, so one thing I think WebSign does want you to be sure and use a capital C. It's not liking a lowercase. It is okay with a negative exponent. So negative x, that right there. Yes, so very, very good question. Let's think about it. If we had used our properties, we could break this apart like this. Okay. Then we would just find an antiderivative for each one of these pieces there. So we would get 5/3 x to the third plus c for this one. And then it would be plus or minus negative 3x to the -1 plus c on that one. Okay, and the idea here is that if we combine those, we would have c plus c. So that would be plus 2c. And since c is completely arbitrary, it can be any constant value we want to, then multiplying it by 2 still means it's still an arbitrary constant. So instead of writing 2c, you just write c. That makes sense, yeah. So whatever operation times c, you can just not worry about it and just write c because it takes care of it. As long as there's not a variable in there. Yeah, so good question there. Okay. All right, so one more thing in the slides. More thing in the slides here. Let's see, so they wrote it as a mixed number, so is that what we get there? 32 and 4. Okay, yeah. Okay, so we're not going to do much with this, okay, in this class. But if we go back to the part 2 of the fundamental theorem, okay, it says this, or we can think about it like this, right? If we integrate the derivative of a function, then we just evaluate the function at both endpoints. Okay. That's the same thing as saying we find the antiderivative of a function. If we start with thinking about it as the derivative initially. Okay, so what this thing's telling us is that if we want to know the area underneath this derivative, okay, between A and B, then it's just function evaluated at B minus the function evaluated at A. So what that gives us, as we think about equating that to some value, what that gives us is the net change. Okay? How much over that interval, how much did that function change? Okay? So if it's linear, that's not impressive, right? Because we could think about if we have a linear function that's always either increasing or decreasing, we subtract the endpoints and we actually get the total change. It's not that impressive. But remember here we're dealing with functions that are curvy, and they're not necessarily linear. So part of the time they may be above the axis, part of the time they may be below the axis. So we've got some increase and some decrease, and then we're figuring out the net change just by evaluating two numbers. And we're not having to do plus this, minus this, plus this, minus this, plus this, minus this over some big interval. We can just start at the beginning and then take the end value and subtract, and we get the net change. So that's really nice. Here's one concrete example here. So if we got a function v of t, it's the volume of water at time t. So we've got that function that models how much water is in this reservoir at a certain time. Then the derivative, v prime of t, okay, would be the rate of change of water. So that would be the inflow or the outflow, okay, at time t. And so then if we are using our fundamental theorem here, if we took two times and we found the integral of change of the volume, okay, all we would have to do to get the net amount that we have changed, the volume has changed, is evaluate the function at time 2 and at time 1 and subtract. So again, if you think about that as linear, that's not impressive, but if you think about the fact that the volume may be going up part of the time and maybe going down part of the time and switches back and forth, then that's really nice. We just have to evaluate the function at two numbers and we get the net change instead of having to total all those things up. So that's really nice there. Okay. Okay, so the plan, I know you got a lot thrown at you today, especially for those of you that have never seen this stuff before. Here is the plan. So Wednesday, I would just help you work on these in the assignment. Okay? So between now and Wednesday, I know that's not a lot of time. Okay, between now and Wednesday, try to knock out the ones that you see how to do and they're not much trouble between now and Wednesday, and then we can focus on the ones that are giving you trouble on Wednesday. Okay? And if you have one that even if you get through it and it still gave you trouble, we'll find another one like it. We'll do another example, that kind of thing. Okay? We just ideally, like if I had it my way, if the world worked Mr. Stanley's way, I would say, okay, here's how you do these integrals. Here's 100 of them. Come back in 2 weeks. Okay, but we don't have that kind of time. Okay? So we've got 16 of them, and you want to make sure you really know what you're doing as you work them. So we'll work on those Wednesday. Okay, try to help you build your confidence up on most things. And then the only thing we have left, okay, is finding integrals, okay, where we're using a different technique, okay, where it's not one that's so straightforward that we can just use one of those rules. Okay. Sadly, even if there are hundreds of these rules out there, there are things that we could want to integrate that we don't just have a straightforward rule for. So we only have, in Cal 1, we only have one extra technique that we talk about. And here it's called integration by substitution. So, and then you get to do, the ones of you that get to go on get to do more later. So, yeah. Okay. All right, well, that's it for today. So work on those integrals, and then I'll help you with those on Wednesday.